We have another full schedule. So the first speaker is Sandra Faber telling us about CANDELS.
Thank you very much. Welcome to everybody. So glad to see you here in Santa Cruz, our annual tradition. This is a talk about CANDELS data, the demographics of star-forming galaxies since C of 2.5. It was the thesis of Jerome Fang, who has graduated and gone on to a teaching position. Briefly, we're at rather low redshifts, 0.2 to 2.5, pretty bright galaxies, H brighter than 24.5, and mass range in the range 10 to the 9 and 10 to the 11th solar masses. So the data used have been published in these two papers. These are CANDELS catalogs, official catalogs on our first two regions. There's photometry-related data, including redshifts and rest frame colors, and also structural data from model fits to images. So let me take my hat off and thank all the dozens of people who contributed to this database. We found it useful to use this coordinate system for plotting. So each individual panel here is an XY plot, and we arrange them in this grid. Stellar mass goes this way, and redshift goes that way. And when you have a grid of plots like that, then you can put evolutionary tracks on them like this. And so these tracks tell you what the average galaxy is doing as a function of time. And what you need to keep in mind, very roughly, is that galaxies tend to evolve at a 45-degree angle in this plot. Much of what I will say depends on conclusions from the UVJ diagram, which turns out to be a very, very powerful tool, maybe even more powerful than its inventors had ever realized. So here we have our mass redshift grid, and each panel is a UVJ panel, and what we've done is we've color coded here by the specific star formation rate. So there are a couple of things that are really evident in this diagram. The first thing that's obvious is that constant values, loci, of specific star formation rate appear as these colors. So star-forming stripes appear in the diagram. Then the next thing you notice is that with time, the colors are becoming less blue and more green and more red. This region up here of red points here are quiescent galaxies. And so star formation is gradually going out over time. And the third thing that you notice is that this depends on the stellar mass. For example, if you look at the combination of colors here, you don't find them reproduced at lower masses until later in time. In other words, the star formation histories are downsizing. Now, it turns out that if you look at all the diagrams at once, this coordinate here going crosswise, which we call u minus v prime because it's rotated in this coordinate system, that coordinate is a good indicator of star formation rate. And here's a calibration of this. This is specific star formation rate this way, and this is this coordinate u minus v prime, and the scatter is 0.2 dix. So all you need to know for a galaxy to estimate its star formation rate pretty well is its position in UVJ so that you can derive u minus v prime. And here is what the specific star formation rate looks like as a function of redshift and mass, the classic pattern with quenching and quenched galaxies. These star formation rates are from SED fitting. Pardon? Up to 20 in some cases, many. Yeah. I should say that the catalogs were derived by having many people on the team use their methods, and then these are medians of all the results, and I think give better results for that reason. We can also look at this grid and color code now by absorption. Absorption is derived also from this SED fitting technique, and what you notice is, let's follow this group of galaxies. They're evolving from here to here to here, roughly. And you can see that their UVJ colors are getting redder as a function of time. And again, that motion is subject to downsizing so that we see greater reddening faster at higher mass galaxies. Now we can clean up this diagram even further if we note that when we plot, this is a new plot, this is each panel is specific star formation rate versus, I've chosen a size indicator, a delta size semi-major axis. What's important to note is that at each redshift mass bin, there's a cloud of points, that's the star-forming main sequence, and below that cloud are a bunch of galaxies with lower star formation rates. Those are presumably galaxies that are on their way to quenching in the Green Valley. And what we see is that they have lower absorption. See, these are blue, whereas those are red and green. And if we get rid of them and replot the diagram, this is what we were just looking at before, but now we've gotten rid of those points. It cleans up nicely, and you can see that absorption, AV, as determined by this method, is very well predicted by just V minus J color. So V minus J gives dust on the main sequence, and dust is the main reason why galaxies are getting redder as a function of time, not so much the dying of star formation, which tends to move galaxies crosswise to the distribution. Now then, we can start to put together structural information together with the photometric information. And so in every mass redshift bin, we can plot mass versus radius and define a delta radius. So this del SMA tells you how big a galaxy is relative to others of the same mass at the same Z. And we can do something similar here also with the specific star formation rate. So we now have two deltas to play with. And I'd like to stress the fact that there is a considerable range in radii at a fixed mass, just roughly plus or minus a factor of 2. Keep that in mind, we'll come back to it later. So now in the same grid, what we're plotting in each panel is the absorption, AV, versus the delta size parameter. And what's very evident is something that I'm calling dust banding. So the points are color-coded here by axial ratio, B over A. And let's focus in one panel on the blue-green points. Those objects are face-on. They look round. They vary in size. And the dust reddening varies as a function of the galaxy size. The smaller galaxies are more reddened, presumably because they have more dust along a line of sight. They're more concentrated. At the same time, we can look in the same panel at the edge-on galaxies. Those are the blue ones down here. And we see that in general, they have higher absorption and show the same size trend. But what's important here is the fact that the edge-on ones are more reddened than the face-on ones. And that, of course, is the characteristic signal of disky galaxies. So let's absorb this pattern. Face-on is less reddened, edge-on is more reddened. That's a sign of disks. With that, we can go back to the main trend here and follow this evolution. Here is a low mass, high redshift sample, and it's not showing that banding. That could be for two reasons. Maybe there are no disks there, or maybe there's no dust there. But as time goes on and those galaxies evolve, they develop dust and or disks, both, and they're both visible here. So the conclusion here, and you can see that all over the diagram, this banding pattern is evolving with time. So the growing dust reveals the existence of disks if they exist. And so with that conclusion, it's now important to look down here. What are these galaxies? These are massive objects between 10.5 and 11 at a high redshift. And what's remarkable here is that they're very dusty. Look, AV is high on average. It just about equals the average of AV up there, but there's no banding pattern. We can enlarge that so that you can see it very clearly. There's no tendency whatsoever of the edge-on galaxies, which are red, to have higher absorption than the face-on galaxies. So this is what's leading me to question whether or not in this high redshift bin there are really disky galaxies. I'll come back to that in a second. Now I'm going to add yet more information on axis ratio. So let's ask ourselves, what distribution do we expect in this coordinate system, axis ratio versus size, if we have a range of disks, each one of which is perfectly thin and we view them from random directions. Well, you probably know that you predict a uniform distribution with face on here and edge on down here. Now, we don't have disks that are infinitely thin, so we can't see objects here, and so they tend to get collected and make a slight bulge here. But nevertheless, the basic pattern is very similar. And what would we expect if we had a bunch of spheroids, prolate spheroids, with an axis ratio of about 0.25? If we looked crosswise at these spheroids, they would look large and elongated. But if we look at them end-on, they'll look round and small. And so prolate versus oblate do very different things in this coordinate system. And at the same time, we can also look at the dust correlations. If these galaxies are dusty, the prolate are going to be very dusty, seen edge on here, whereas the oblate are going to be low dust because they're seen face on. So with that information, let's now ask ourselves what we're actually seeing here. Here's our coordinate system, and I'm coding here by the amount of dust. So we just saw good evidence for disks in this particular panel, so let's blow it up and think about it a little bit more. All right, so for the massive, for the large galaxies, I'm going to block out the small ones. Okay. Just look at this region of the diagram. It looks plausibly as though we've got disks here. Down here, when we see edge-on galaxies, the absorption is high, and when we look up here, the absorption is low. So a good interpretation for a pattern that looks like that is disky. Looks as though when we see them edge on, we get a little bit larger radii, maybe because we have larger lines of sight through the disk. So it's not perfectly a vertical distribution, but nevertheless roughly not bad. And if you now look around the diagram, you can see that replicated at later times. But when you look at early times, you don't see a pattern like that. This corner is missing. That's a telltale signature of not having disks. And now, since I raised questions about this panel, let's look at it. Bring it forward. Okay? And again, I think this one is problematic because I expected to see, if this was a disk pattern, I expected to see these more heavily reddened than those, and we don't really see any trend at all vertically there with reddening. Okay, so I'm leaving you with the fact that there's no AB trend with B over A in massive galaxies at Z of 2 to 2.5. So I do not understand the structure of these galaxies. Moving on now to my last point, let's look at the variation of specific star formation. Plotted again versus galaxy size. I want to blot out from your consciousness all of these galaxies that are fading, going towards the green valley. So let's just get rid of them and focus on these distributions, which are the star-forming main sequence galaxy ridgeline. Look at those only. And just reminding you of the fact that there's a substantial variation in size here. There's no noise in these size measurements. You look at a big galaxy and a small galaxy, it's clear that they're very different. Now, what I want to call attention to is the fact that there's no trend in any one of these panels of star formation rate versus galaxy size. And that is a little puzzling because supposing we thought that the star-to-gas makeup was the same in all of these galaxies, then we would expect a trend because we are concentrating the gas and because the Kennicutt relation, when you use total gas, predicts a slope of 1.4, not 1. And when you go through the math, you can calculate that the small galaxies should be making stars more rapidly, and this is the trend that you predict if the gas-to-star ratio was constant in one of these panels. And clearly we don't see that trend, so that's if the relationship is held by all of these galaxies, that's evidently the star-to-gas ratio is varying, and when you work through the arithmetic, you conclude that these things have about half the amount of gas-to-star ratio as those guys. Factor of 2 pretty much takes care of it. Now, we've also looked for other trends to explain why some of these objects are high and others are low. The question before us is, the main sequence has some scatter. Can we identify a reason why it has a scatter. And I just investigate radius. That has no effect. We also have Sirsic indices measured, and we have this central density sigma 1. We've looked at both of those, and there's no trend with either one. So we have not found any structural parameter that correlates with this delta specific star formation rate. And that's what has led me to think that perhaps there's another way of thinking about this. You heard about this yesterday when Aldo talked about the shark in the bathtub. Let me pause for a second and just say that when I've thought about the Schmidt-Kennicott relation in the past, I thought that nature provided the gas in the x-coordinate, and then the law told you how the star should form. I'm now thinking that's not the case. I'm thinking maybe nature provides the gas coming in that needs to make stars, and then the surface density in the galaxy arranges itself according to the law in order to make stars at the same rate. In other words, this model is saying that a galaxy, the rate at which it makes stars has nothing to do with what it's doing on the inside, but everything to do with the rate at which halo mass accretion is delivering gas onto the galaxy. That's what this model says. And as we were discussing it, we noticed that this scatter here, which is about plus or minus 0.3 dex, is very similar to the scatter that's observed in the halo mass accretion rates. And with that observation, we sort of took off and began to make some other calculations that will be interesting to pursue. Okay, so here's my summary. The UVJ diagram gives specific star formation rate and dust. If you add an axis ratio, you get an entirely new disk indicator. There are a whole host of things that seem to evolve together, and I've called it the star formation cycle. It's the star formation history, the overall arc, the production of metals that are enriching the interstellar medium, and that in turn makes dust. And all of these things increase as a function of time, but they go faster in more massive galaxies, and that's what we've come to term downsizing. There's a separate structural cycle, though, which has something to do with disk settling. And disks appear strongly later, only at around a z of 1.5 in these data. There are few disks at z greater than 2 at any mass, and moreover, the disk formation is tied to redshift only, not mass. It's not subject to downsizing. A point that I should have emphasized more as I went past the slide was the curved boundary to them. In fact, let me just run back on because it's so important. It's one of my major points that I wanted to make. Here we go. There, okay? When we looked at this before, I encouraged you to look at this part of the diagram, which I encouraged you to think was largely disky galaxies seen at various angles. But now returning to these diagrams, I want to emphasize the fact that every one of these has a curved bottom. And we know that these regions are not empty because of observational bias. We can see these galaxies if they exist. They just don't exist. And so the takeaway message as far as the axial ratio size distribution of galaxies is that it's a very, very complicated situation. And probably the best interpretation for those data is to say, yes, those are all disk galaxies, but as we go to smaller ones, we see rounder ones. There is a correlation between size and shape. And the reason why this is important is that it's not valid anymore simply to look at histograms of B over A, as has been done to deduce galaxy shapes. That is not valid because we actually have different kinds of galaxies in this distribution. It's going to require a much more sophisticated analysis, probably guided by theory. Okay, so let me go back to my conclusions, which I had almost finished. This is my last point, that the smaller, among star-forming galaxies, smaller galaxies are intrinsically rounder, and therefore a B-over analysis has to be redone to take this into account. Final point here is residuals on the main sequence are independent of radius, Sirsic index, and central density. I was listening to Avishai's talk yesterday, and he would like us to think that galaxies are bouncing up and down inside the main sequence because of compaction. I do think they are bouncing up and down within the main sequence, but I haven't seen any evidence so far that this bouncing is associated with compaction. I think departure from the main sequence is so associated, but not the bouncing. And so this is something we need to look into further, look at the model galaxies and try to figure out whether or not we could see structural signs of bouncing amongst galaxies that are on the main sequence and not leaving it, but moving up and down. Thank you.
Lots of questions, we have time. Let's start with Avishai, then Reinhardt, then Mark.
So I do think we do have evidence, and the evidence was seen in Linda's talk and Reinhardt's talk and others. So there's one component which you did not look at, the gas. And what we see in these compaction events going up and down is a wet compaction. It's the gas becoming compact, first of all, then the stars form and remain compact, but the gas go up and down. So the main feature, and I bet that if you look at the gas, you will see gradients across the main sequence. And Linda and Reinhardt and others see it in depletion time and in gas fraction. Very clear gradient. And this is very consistent with the simulations. So I think that's what's missing, and the next step, I think it will be seen.
Comment? Very briefly. I think that those correlations exist, and they would exist even if galaxies went up and down across the main sequence just because gas is burying and falling into them. The key thing that I take as part of your theory is really the structural implications.
The stars become compact and stay compact. So you're not going to see a big gradient. This variation in the stars, you see it from each time the gas.
Okay, next question.
Well, Sandy, let me first say this is a wonderful, new, innovative way of looking at galaxy populations. Very impressive. I'm looking forward to your paper. On the issue of the variation of extinction and the issue of diskiness, I would like to offer you a way out, which you presumably already have thought about. So your view very clearly assumes that you have a light source, distributed light source, shining through a disky distribution of dust. And then you get these features which you described. But suppose now you have a totally different way of distributing the dust, which is, instead of a diffuse disky distribution, you assign to each stellar component, cluster, think of clusters, a very optically thick local source of extinction, which typically in the business people call the birth cloud dust. And suppose the diffuse component is not that important at high redshift. It's this birth cloud component, which is highly optically thick, such that the optical depth can really be very substantial. But then, of course, it doesn't depend anymore on any orientation. It's just, the local dust component.
Yeah, that's certainly possible. I would say that the information from the A over B over A distribution is also an interesting component in the modeling. They have to be modeled together. There aren't very many galaxies in that panel. We need to look at our 3 other fields and do a statistical analysis.
Okay, we still have a lot of questions. Could the next speaker come down and connect their computer? And Mark was next, and then we'll take one more.
Right. Sandy, going back to your comments on the Kennicott law and the slope you were expecting to see but didn't, I just wanted to point out that if 1.4 is actually a little bit too steep a slope, in part because that's being driven by, at the low end, including the H1, at the high end, sort of starbursts versus non-starbursts, if the slope is a little flatter, then it gets a lot easier to understand why you didn't see anything. And moreover, then your sort of shark in the bathtub model becomes extremely simple, and it is just, there's a constant depletion time. And so star formation rate is just equal to just scales with gas supply, and that varies as the cosmological accretion rate does. So it's just gas supply goes up and down as the accretion rate goes up and down.
Right, so the model could still be right. The only thing that would change is that particular justification for it, that the lack of the observation implying that the model must be right. That piece of evidence would disappear. But you can see how well we determine those slopes. And so even if you were to go from 1.4 to 1.2, the effect would be half as large, and I would claim we still don't even see that. So it's really profoundly flat, the relationships that we are seeing.
Okay, one last quick question from David.
Yeah, I was thinking that the bottom right panel that you were showing that is a bit puzzling,
yes,
because it's not connected to orientation, may be connected to the fact, so this is I0 on redshift 2 and high masses. These are typically clumpy galaxies where you may expect most of the obscuration to be 3D. At smaller scales around the...
I think that was Reinhardt's point.
Ah, sorry. Okay, I agree. Sorry.
Okay, we have lots to do.
Much of what I will say depends on conclusions from the UVJ diagram, which turns out to be a very, very powerful tool, maybe even more powerful than its inventors had ever realized. So here we have our mass redshift grid, and each panel is a UVJ panel, and what we've done is we've color coded here by the specific star formation rate. So there are a couple of things that are really evident in this diagram. The first thing that's obvious is that constant values, loci, of specific star formation rate appear as these colors. So star-forming stripes appear in the diagram. And then the next thing you notice is that with time, the colors are becoming less blue and more green and more red. This region up here of red points here are quiescent. CANDELS catalogs, official catalogs on our first two regions. There's photometry-related data, including redshifts and rest frame colors, and also structural data from model fits to images. So let me take my hat off and thank all the dozens of people who contributed to this database. We found it useful to use this coordinate system for plotting. So each individual panel here is an XY plot, and we arrange them in this grid. Stellar mass goes this way, and redshift goes that way. And when you have a grid of plots like that, then you can put evolutionary tracks on them like this. And so these tracks tell you what the average galaxy is doing as a function of time. And what you need to keep in mind very roughly is that galaxies tend to evolve at a 45-degree angle in this plot, at u minus v prime, and the scatter is 0.2 dix. So all you need to know for a galaxy to estimate its star formation rate pretty well is its position in UVJ so that you can derive u minus v prime. And here is what the specific star formation rate looks like as a function of redshift and mass, the classic pattern with quenching and quenched galaxies. These star formation rates are from SED fitting. Pardon? Up to 20 in some cases, many, many. Yeah. I should say that the catalogs were derived by having many people on the team use their methods, and then these are medians of all the results.
We have another full schedule. So the first speaker is Sandra Faber telling us about CANDELS.
Thank you very much. Welcome to everybody. So glad to see you here in Santa Cruz, our annual tradition. This is a talk about CANDELS data, the demographics of star-forming galaxies since C of 2.5. It was the thesis of Jerome Fang, who has graduated and gone on to a teaching position. Briefly, we're at rather low redshifts, 0.2 to 2.5, pretty bright galaxies, H brighter than 24.5, and mass range in the range 10 to the 9 and 10 to the 11th solar masses. So the data used have been published in these two papers. These are galaxies. And so star formation is gradually going out over time. And the third thing that you notice is that this depends on the stellar mass. For example, if you look at the combination of colors here, you don't find them reproduced at lower masses until later in time. In other words, the star formation histories are downsizing. Now, it turns out that if you look at all the diagrams at once, this coordinate here going crosswise, which we call u minus v prime because it's rotated in this coordinate system, that coordinate is a good indicator of star formation rate. And here's a calibration of this. This is specific star formation rate this way, and this is this coordinate.